next thing we're going to look at is acid-base reactions. So acid-base reactions come up an awful lot, very, very important, and they come up a lot in writing balanced equations. So common acids that we should know: hydrochloric, nitric, and sulfuric. And then from our organic side, we may also have done a little bit about ethanoic acid. So hydrochloric, nitric and sulfuric are strong acids, what we call our bench acids, the ones that we use in the lab all the time, and then ethanoic acid is just an example from the organic world, and we won't look at the equations for that today. And then our bases are basically all going to contain a metal and oxygen in some way. So we have a metal oxide, metal hydroxide with an OH group in it, and a metal carbonate. And that's all we're going to stick with for the bases. It's not the only thing that reacts with acids. So acids also react with metals. We're going to look at that when we do redox. It's a slightly different type of reaction. So the important thing is that my acids all contain hydrogen, and then they will start with hydrogen. Ethanoic acid is slightly different, but certainly my lab acids do. And then all my bases contain a metal and something with oxygen. So either just oxygen on its own, hydroxide is OH, carbonate CO3. So they all have oxygen component. And what we should know is that when they react together, you get salts. So the reason you get the salt is that the non-metal part of the acid, or the non-hydrogen part, the chloride, the nitrate part, and the sulfate combine with the metal. So it's like the metal and the hydrogen swap places. So if we react with hydrochloric acid, we get a chloride, a nitrate, or a sulfate, depending on the acids. If we react a base with ethanoic acid, we make metal ethanoates or ethanoates. So it's the same idea. We've taken off the ic, like nitric becomes nitrate. So ethanoic becomes ethanoate. That's how we name the salts from organic acids. But we also make the other products. We make water and we make carbon dioxide. Now we really tend to focus on the salts because this topic comes up with creating salts, making salts, preparing them, making soluble salts, things like that. But actually, that's not what neutralization is. The salts don't really come into it, they're spectator ions. So we can write ionic equations for acid-base reactions. We don't have to do it very often, but if we get used to seeing it, it's going to help us balance the equations. So let's have a look. Well, our acids contain hydrogen in the form of the hydrogen ion H+. Our bases contain oxygen, either in the form of the oxide ion O2-, the hydroxide ion OH-, or the carbonate ion CO3, 2-. So we could write equations for how they react, the products that they make. So the other parts, like the chloride and the metal, would make the salt. This is the part that makes the water and or the carbon dioxide. So they come together. The main process in an acid-base reaction is that the hydrogen from the acid comes with the oxygen from the base to make water. The only exception to this is ammonia, which you will do more about at A level but isn't touched on much at GCSE. So ionic equations. If you have an oxide, let's have a look at what the ionic equation would look like. Well, your oxygen has a 2- charge, and there's 1 oxygen in water but 2 hydrogens. So if I'm reacting it with an acid, I'm going to need 2 hydrogen ions for every 1 oxide ion. Let's have a look at the ionic equation for hydroxide. Well, hydroxide already has a hydrogen in it, and it only has a 1- charge. So I only need to add 1 H+ to my OH- to make water. This is something you see also happen in electrolysis when the hydrogen and the hydroxide ions split up in water, and that's why water conducts electricity slightly. And then carbonates Well, a carbonate looks a little bit more complicated. So the ionic equation involves lots of other things. You've got CO3 2 minus, and we're losing CO2. Now that's one thing that's usually easy to remember. So the way to look at it is that a carbonate ion is actually made of CO2, a neutral molecule with 1 carbon and 2 oxygens. If you take that away from CO3, you've got an oxygen left, and you've got a charge because there's no charge on CO2. So actually what you now have is the same equation as the top. It's an oxide ion with 2 hydrogen ions making water, and the CO2 comes off separately. So those 3 equations tell me that every time I react an oxide, I need 2 H pluses for every oxygen. If it's an OH, I need 1 H plus for every 1 OH. And if it's a CO3, I need 2 H pluses for every CO3. That's going to really help me balance acid-base reactions. So what we're going to do now is apply those ionic equations and see how they can help us balancing the equations for acid-base reactions. So here's my first example. I've got sodium hydroxide, NaOH, so it's got 1 hydroxide there, and I've got H2SO4, so sulfuric acid has 2 hydrogens in it. Notice I'm just ignoring the sulfate bit at the moment. I'm not worried about it. I want to worry about the hydrogen and the hydroxide. So if I've got 2 H pluses, I know I need 2 OH minuses, and the only way I can do that is to put a 2 in front of the whole NaOH. Now it turns out that that has sorted out my sodiums, because there are 2 sodiums there. And the only other thing I need to think about was if I had 2 OH minuses and 2 H pluses, then I'm going to make 2 waters. So that's one example. The next one I've got this time, it's a carbonate. So carbonate, remember, is just like oxide, it's O2 minus. The CO2 has come off over here. So it's just the 1 oxygen that has ended up on the right-hand side in the water. But it's H2O. So for every 1 oxygen, I will need 2 H's. HCl only has 1, so I put a 2 in front. And actually now, this equation is completely balanced without having to worry too much about it. Last example, just to show that it works really well, even if it's a little bit more challenging. So again, I've got 1 hydrogen in my acid, because it's HNO3, and I have 3 oxygen or 3 oxide ions in my aluminium oxide. So I'm ignoring all the oxygen that's in my NO3 because you can see NO3 stays together, like it doesn't change in the reaction, the oxygen doesn't get lost. Not like CO3 up here where it's actually part of the chemical reaction. So 1 H plus there, 3 O2 minuses. Every O2 minus needs 2 H's to go with it. So every O needs to go in a water. So if I have 3 oxygens in my base, then I will have 3 waters. That means I now need 6 hydrogens. There's only 1 in every hydrogen nitrate or nitric acid. So I need a 6 in front. Having done that, everything should nearly be now balanced except for the fact that I've got 2 aluminiums here and I now have 6 nitrates. So I'm not counting those oxygens separately. I'm not doing like 6 times 3 is 18 or anything like that. I'm just going, there are 6 NO3s. Over here, that's easy because I've got 1 aluminium and 3 NO3s, 3 nitrates. So I'm just going to put a 2 in front. That now gives me 2 times 3, 6 nitrates, 2 aluminiums, and it's balanced. If you're finding an acid-base reaction really, really challenging to balance, the most likely thing is that you've got a formula wrong. So if you wrote it yourself, something's wrong. For example, a common error would be to write CaCl and forget that calcium's in group 2, or to write NaSO4 and forget that sodium's a 1+, sulfate is a 2-. So watch out for that when you're balancing those sorts of equations.